So we will move on with calculating the other two parameters, d and theta. So let's start with d. d, now we switch and we discuss about the distance between the subsequent x-axis along z-axis, right? Small difference here, and what you have to be careful is that the distance between xi and xi plus 1 is measured on zi plus 1, right? Not on zi anymore. Why is that? If you remember, xi is perpendicular to what? Right. And xi plus 1 is perpendicular to?
zy plus 1 and zy plus 1.
Right. So zi plus 1 is basically perpendicular to xi and xi plus 1. Because xi is perpendicular to zi and zi plus 1. And xi plus 1 is perpendicular to zi plus 1 and zi plus 2. Alright, so zi plus 1 is perpendicular to x1 and xi and xi plus 1. Therefore, we can calculate the distance along that axis again, right? Since we put the x-axis according to the convention, we can measure this distance. So let's have a look. Now we have distance between x0 and x1 along z1. So it's basically this distance here, because this is z1. z1 is pointing upwards, right? So before we had distance between z0 and z1 along x0, so it was this distance, now it's this distance. All right, so let's say, I don't know, another 2 centimeters. In our case, 3, I don't know how much it is. D1 is distance from x1 to x2 along z2. So it's basically this distance, right? Now both of these are in the center, so normally there shouldn't be any distance. I'm rotating a bit so you see. They're both here basically, so there's no distance in this direction, right? We could have left the axis here, it would have been a bit more complicated, but anyway, I think it's simpler if we say, okay, they're here, so the distance here is 0. Then I have x2 and x3 along z2. So where is it? Sorry. Am I looking at the right axis? No, something is fishy here. So z2, so 0, 1, 2, 3. Yeah, along z3. So it's basically so x2, x3 along z3. So it's basically this distance, if there was any, right? How they are on this axis. Let me rotate it so you see it better. So x3, sorry, 0, 1, x2, x3 along z3. So it's this distance, okay? Which is 0 because they intersect here. Okay, so 0 as well. Then we have x 0, 1, 2, 3 to x4 along z4. It's basically this distance between these two, which is 0 as well. It's a lot of zeros. Then we have x4, x5 along z5. Basically here, because that's where x4 is, x5 is, right? So it's this distance to along z5. x5 is up here because it's perpendicular to z5 and z6. And that's why it's here. So this is the distance. I just couldn't print it there. Maybe I can improve this. Sorry. So this is not 0, it's, I don't know, some 5 centimeters, let's say. Then we have x, let me rotate this one, x5, x6 along z6. And what do we have here? This distance? Yeah, this one. This distance here. Now, because I'm moving, it's from this one to this one, and the positive z is pointing there, this is a negative distance. Okay, so I might have a negative distance somewhere. Okay, so let's say -2. And then I have x6 to x7 along z7. How much is this? Is this distance, right? Let's say 6 centimeters. 5. That's bigger. That's smaller, right? So this distance is variable because the x-axis, the x6 is attached on this joint and x7 is attached and this link, sorry, after the joint, and this basically translates, right? So we have something changing here. You see this distance is changing. But it's only changing for this joint because this is a prismatic joint. For the other ones, these distances don't change. So when this axis is moving, let's say, this distance does not change between this and this x, right? Along this axis, because the axis of rotation, right? When this joint is, sorry, remove it. When this joint is rotating, sorry, the distance between these two x does not change, right? Obviously, it's the same around these z's that we didn't discuss, but yeah, these distances don't change, or the angles, as you see. Okay, but for prismatic joints, the distances between the x-axis changes, right? And it's variable, so we don't have a fixed value. So we call this the variable of the joint. We usually symbolize it with Q and the number of the joint. So this is Q, let's start from 0, so this would be Q6. Right? This is 0, 1, 2, 3, 4, 5, 6. Okay? And it's variable. So I don't know the value beforehand. It changes. Something has to change. For the last one, we'll see again. All right. Clear with the d parameter as well? Distance from xi to xi plus 1 along zi plus 1. What would be the last parameter theta? The angle between these two x-axes around the zi plus 1. Okay? Good. So we work again with the same axis, x0, x1 around z1. How much is this angle basically? How much is it? Huh? Pi over 2. So this is 0 and this is 1. Sorry? So they both point towards you. So it's 0. How much is it now? Don't look away. So it's x0, x1. 90. How much is now? Minus 90. How much is now? Right? So what do we see here now? As for the prismatic joint, this distance was variable. For the revolute joint, we have some variable as well, which is an angle, and it makes sense because it's a revolute joint. We have rotation, right? And it's the angle between the x-axis, as it was the distance between the x-axis for the prismatic joint, right? So this is not a fixed value. It's variable, okay? We say that based on these numbers, we contrast transformation matrices that we multiply to calculate forward kinematics. So if all these numbers would be fixed values, the forward kinematics would be based on fixed values, so nothing would change, but something has to change. And this is D for prismatic joints. You see all of these are revolute, and they had fixed values for D. So the distance is between x-axis, besides for the prismatic joint. And we'll see that for theta, it's the revolute joints that have a variable here, right? So this angle, you see it visually as well, that this angle is changing when I'm moving Q0, right? Now, you said that this is 90 degrees, positive 90. Why? Because I'm rotating around this axis, right? And positive rotation is this one, right? You remember at the beginning we said that we put the z-axis the way we consider the positive rotation to be, right? If this is positive rotation for a robot, then I'm going to put the z-axis pointing upwards. So this comes back now as well, right? That this Q0 will be basically the rotation around this axis, and it's going to be positive when I rotate like this. It's going to be negative when I rotate like this. So here I can come and put Q0, all right? Now, what is theta 1? It's the angle between x1 and x2 around z2, right? What is this angle? This and this around z2?
Minus
90. How much is now? How much is now? 90. But basically it is a variable, and it's the angle will change based on how much the joint moves. So it's basically the joint angle, right? So again, I have here Q1, right? What is the angle between x2, which is this one, and x3 around z3? I have to. This one varies more than just the joint, so it has some random effect, chaotic, I don't know, whatever. But yeah, the idea is that it moves. It moves together with this joint. Why does the x moves together with this joint? How did we define this x? To this and this, right? So when this joint moves, this axis moves as well, and the x has to stay perpendicular to both of these, right? And you see that it's basically the x rotates so that it stays perpendicular, right? Right, and as it rotates, then the angle between this axis and this axis also changes around this axis. Clear? Plus some random effect. Right, so here again I have Q2. 3 would be Q3, so that's basically the angle between X3 and X4 around Z4, so it's basically this rotation, and again you can see if I rotate, no, this is this one, sorry. X3, X4 is this one, so I forgot about this one. Right, you see I have, again, this X rotating around this axis with a joint angle, Q3. Q4 would be this rotation between these two X. All right, Q4. Q5 would be the rotation between this and this around this axis. So this rotation, Q5. and then Q6, theta 6 will be the angle between x6 and x7. And here you see I don't have, okay, now I made a mistake, but yeah, here you see that I don't have any rotation with this when this one changes. So for the prismatic joint, I will not have a variable here because there is no change between the x-axis, the angle between the two x-axes. There is a change in the distance between the two x-axes. Right, so here I will have, in this case, what's the angle between x6 and x7 around z7 is 0, or it looks like it's 0. All right? Good. So, for prismatic joints, I calculate r and alpha the same way for all the joints, and d and theta for all the joints, but if I have a prismatic joint, d will be a variable, the joint coordinate, the joint length, right? If I have revolute joints, theta will be a variable, will be the joint angle, okay, always. So basically for 6 joints robot, you don't have to calculate 24 parameters, like 6 times 4. You have to calculate 6 times 3, so 18 parameters. The theta or the d you get for free because it's a variable. Okay? Great. Now, I say that there is 4 plus 1 parameters because we also have the offset. So what about the offset? What is the offset? And I think the easiest joint that I can demonstrate what is the offset is the prismatic joint. It's basically what is the distance, in this case, what is the variable when the joint reports 0 value, so when it's like at 0 position. So let's say in this case you can imagine it when it's fully retracted, right? I still have a distance between these two axes. That is my offset, that I always add to the Q6 to calculate the transformation from this frame to this frame, right? I have to add this translation around Z. Otherwise I will make it wrong. So this is my offset. The distance between the subsequent x-axis when the joint is at 0 extension, let's say, for a prismatic joint. Okay? So I will, let's say if I move the joint by 1 centimeter, then the overall translation will be the offset plus this 1 centimeter, right? That's why it's called the offset. So in this case, I don't know, it's like 7 centimeters. The same concept is used for revolute joints, right? What is the angle between the subsequent x-axis when I consider the joint to be at 0? So let's say my robot is at 0 position when I'm like this. Let's pull this up. I'll remove this, it's too dangerous. And let's say this is like this, and this is like this, and this is like this. Let's say this is when I program the robot and I put Q0, Q1, Q2, all the Qs to 0, it will stand like this. All right? The offset for the revolute joints will be the angles of the x-axis at this configuration. Right? So what would be the offset for the first joint, for Q0? Is the angle between x0 and x1. How much is it? Around, again, z1, sorry. 90 degrees. So the offset here, it's 90 degrees. So consistent. Okay? That's what the offset is. Like in the robot in the lab, I told you the 0 configuration is when it's like, I don't know, this L shape, inverse L, whatever, how you call it, right? If you remember last week. Okay, what is the offset for the second joint from x1 to x2 around z2? Pi over 2. Great. If I would have considered the 0 position to be, I don't know, like this, for whatever reason, then it would have been pi. Or if it was like this, then it would have been 0. But let's say I consider it to be 0 like this. So x2 to x3, 0, x3 to x4, pi, they're negative, positive or negative, pi.
The same.
You learn from your past experiences. X4 to x5, pi over 2, right? It's x4, x5 around z5, pi over 2. x5 to x6 around z6, sorry, it's this one. Let's say it's like this, just to make it more fun, or yeah, whatever. Let's keep it like this. Then this is pi over 2, sorry, positive is downwards. And for the prismatic, we already discussed that it's 7. Okay? That's what the offset is. What is the angle between subsequent x, or the distance between subsequent x for prismatic, revolute or prismatic respectively, when I consider the robot to be at its home configuration, or when all the joints are at 0. All right? Good. Now, if I know these numbers, I can calculate the transformations from one frame to the next for subsequent frames, right? And we said that we have basically 4 transformations. So I'll go back a bit. Here, we have 2 rotations and 2 translations. 1 rotation and 1 translation around x axis, and 1 rotation and 1 translation around the z axis. And the rotation will be by alpha and translation by r, so these values. The rotation around x and translation around x, and the rotation around z and translation around z will be by theta and d, these 2. Here, if I want to be a bit more correct, I should add the offsets as well. So theta plus offset, d plus offset for revolute and prismatics. All right. So how does this look like? You can imagine we have an initial frame here and a target frame here, so it's the thick ones. So I have this small animation here that shows you how it goes. So I first have a translation around x, then a rotation around x, then a translation along z, and then a rotation along z, around z, right? So let's play it again. So I have a, oh, it stays a bit and then I can play it again. So I have a translation about x, a rotation around x, then from the right a translation along z, and a rotation along z. And it always, the translation and rotation happens along the new frame, right? So I move along the x, and then I rotate around the new x, which it's the same as the old x, yeah? But then, if you see, I will translate along the new z, right? Which means I multiply from the right, the z transformation. And then I rotate along the new z. So if I see again my things here, I do a rotation around x, then from the right a translation around x. So here the order can be swapped as we discussed last week. But then on the resulting frame, I multiply from the right a rotation and translation around z. Again, this can be swapped because they're on the same axis. Okay. One last thing. I kept on saying that we'll see about the end effector, we'll see about the end effector. We could calculate the DH parameters from the last frame to the end effector frame as well, right? And we can do that. But basically, this is a fixed transformation. There is nothing changing between this frame and this frame, right? There is no join, nothing can move these two frames relative to each other, right? In that sense, we don't deal it as a Denavit Hartenberg transformation, because there we need to have like, okay, we have to place the z-axis along the joint, the axis of rotation or translation, and we don't have a joint here. So it's not technically a Denavit Hartenberg transformation, but we still need to calculate for this transformation. So we need to account for this transformation, so we calculate the forward kinematics until the end effector frame. So once we calculate the overall transformation from the base until the last joint, then I need to multiply from the right one final transformation that takes me from this frame to this frame. And we call this the tool transformation. Okay? And you will see this really in the lab, because you have to define it differently for the robot that you will build. So in this case, what is this transformation from this frame to this frame? How do I need to rotate this frame in order to reach this one? Is this visible actually, this one? So I need to do a rotation by Z with 90 degrees. So if I do this, these two will be aligned. Of course, you have to imagine the green axis too, right? Which we said we don't put it, but yeah, these will be perfectly aligned. If I do a rotation around Z by 90 degrees. So here I have a RZ by 90. All right. And then I can do some translation, either if I depends on these distances. I might want to go down and left, backwards. So I might want to have another translation on Z, let's say by -1, translation on X by -1. This is -1 as well. So I want to go down and back, but this is specifically to this distance, right? But this transformation is fixed, it doesn't change, right? There is no variable here, there's no Q. It's always the same, because as I demonstrate here, yeah, the transformation between these two frames cannot change. It's fixed. Right? Any questions? No. Let me put you some questions, philosophical. Right. Here we said, let's say when we're putting this x-axis had to be perpendicular to this z and this z, and we said, okay, we can put it wherever we like. Would anything have changed if, let's say, I would have put it like this instead of like this? What would have changed? The angle between them, which is where? Not Q6. Q6 is the distance between them, because it's prismatic. It was this angle, right? Theta 6, right? Which was 0, because it was like this. And now it's like this. So now it would be 90, right? Would that be the only thing that changed?
Yeah, the distance would be the same.
The distance is the same, right?
And the last transformation.
Which last transformation? The tool transformation, right? Here I wouldn't have had this one, because now these two are aligned. So I would have had one transformation extra here that I wouldn't have here, right? So it's as if moving this thing from here there. And this is rotation around Z, so it would be an RZ by pi over 2, so it's the same thing, right? I can put it here, or I can put it here. No, because what am I calculating here is the overall transformation from this frame to this frame by taking steps, right? I might take another step somewhere. So let's say I want to go to the wall. I can go all the way straight, or at some point I might decide to go right and go straight. At some point I have to go left in order to reach the same. So if I take an axis differently, it will cause an effect here, I don't know, with a minus or a plus somewhere, but then it will be cancelled by another minus somewhere else, or by another angle or transformation somewhere else. Right?
So it's the same.
So it's the same, right? So it doesn't make sense what happens in between, how I put this one here. It doesn't change the transformation from the base to the end effector, right? If I would change the end effector, yes, I would have a difference, right? Or if I would change the way I put the base one, let's say I would put the Z on the other way, which I cannot because of magnetism, then I would have had a slightly different result. But if I change these frames that we choose arbitrarily, the x-axis, for instance, when I have intersecting z-axis, then it wouldn't change the overall result. It shouldn't change it. Right? All right, so let's quickly go through the rest. 14 slides. Basically here I have a lot of examples, 4 examples, which I thought maybe we'll do together, but I think this was more useful. It's the same thing we see, we would have seen how we do it in 2 dimensions, but it's a lot of confusion about how the axes go and so on. We don't have time to do this, but I have the solutions on the slides. So here we have the robot, so you can try to practice at home, and then we have one solution for this robot. As I say, one solution because again you might decide to put the x-axis differently from how I put it there, right? How do you read this? Again, we have the table dr alpha theta, and then we have the fixed frame with the red, and then each frame has different colors. So I don't use the red for X, blue for Z, just to be clear which frame is what. So because here I have, let's say, 2 frames, and if I had the 2 X axis red, it would be confusing. So I chose to color them differently. And then here also these colors show you, okay, how do I go from which joint to what joint, and what is the calculated parameter. Here on the last row I have the tool. I didn't put it separately, but yeah, this gives you basically the transformation for the tool from 4 to 5. And there are 4 examples. This is the robot we saw also last week, if I'm not mistaken. And this one we saw last week, so you should understand how the joints rotate. If not, then you can see the axis, how I put them. Right? And yeah, there are 4 examples, I think. Oh, 5. 1, 2, 3, 4, 4. All right. Hopefully it's useful. Right? This thing will be in the lab from now on, the robot. You also have the frames in the lab. You will practice doing the Denavit Hartenberg on the robot, on the lab, so it's 3D stuff. So hopefully the 2D stuff will be easier to understand. What I want you to remember is that for revolute joints, the theta will always be the variable, and for prismatic joints it will be the d. All right? One last thing before I let you go is that this is one way to define the Denavit Hartenberg parameters. There is an alternative form. This is basically called the modified DH. This is the pure DH, but I find it less intuitive. I basically show it here for completion, just so you know. If at some point you learn about DH the other way, you don't think I was telling crazy things. It's the same idea, it's just that instead of going from 0 to n, we go backwards, kind of. So basically, its x-axis is perpendicular to the previous z, and the parameters are calculated slightly different, but it's the same logic. We have two lengths and two angles measured around the same axis and so on. And obviously, because it's a different way of going from one frame to the next, we have a slightly different version of the transformation from one frame to the next. It's the same thing but with a different name. All right. So with this we complete the forward kinematics discussion until we build great robots. From next week we're going to talk about velocity, the other part, considering kinematics. Any questions?